Good morning, everyone. My name is Haoran from Huazhong University of Science and Technology, and now I work in Huawei. Today, I will present this joint work with Qiang, Jiang, and Wang about the power management for the green data centers. Modern data centers are consuming increasing amount of electricity and make IT companies the biggest greenhouse gas emitters. To this end, renewable energy-based solution gains a lot of attraction in both industry and academia. Many cloud service providers such as Apple, Google, and Microsoft have built their own data center power systems using renewable energy from sources such as wind and solar. However, the maintenance and upgrade of the underlying server system, for example, server replacement due to failures, capacity increases, or migrations, make data centers heterogeneous in their key processing components. As the requirements of big data processing and AI computation are growing, the data centers have deployed high-performance computing platforms and domain-specific accelerators such as GPU, TPU, and FPGAs. So in the next, I will present how such heterogeneity affects the power management and the application performance in green data centers. First, we introduce a new metric called effective power utilizations, and it describes how much power is used to generate the computing throughput by the power supply. And then we use two heterogeneous servers and a fixed power budget to conduct an experiment. In these two figures, we find that both EPU and workload performance can achieve best results when the power allocation ratio is 65%, as the red box indicate, and not 50% ratio that traditional uniform strategy will choose. In addition to the fact that different servers configurations will affect the allocation ratio decision, the workload features and variable renewable power will also pose great challenges. To this end, it is necessary for us to propose such adaptive power management approach to deal with these challenges. Next, let me introduce our design called GreenHetero. This figure shows an overview of the GreenHetero controller. This controller determines the power source selection and the server power allocation, and consists of three main functional modules, including monitor, adaptive scheduler, and enforcer. The monitor collects the data of power source supply, server level power consumption, and application performance, and then report the data to the scheduler. With the performance and the power state feedback, the scheduler determines the best power source and the optimal power allocation ratio. The enforcer is responsible for implementation by power source controller and server power controller. The scheduler is the most important part of the whole controller. It controls power predictor, database, problem solver, and decision output module. The predictor uses a time series prediction method to predict the energy supply and server power demand. Based on the prediction value, the current power source will be determined. There are three cases to discuss here. In case A, when the renewable energy is sufficient, it will supply the rack independently, and the extra power will charge the battery. In case B, the battery and the renewable power will supply at the same time. In case C, when renewable energy is not available, the rack is powered by batteries. In all cases, when the battery runs out, the grid power is the final power to supply the rack. The database is designed to deal with the challenges of underlying server heterogeneity and workload variability. With the limited profile data, GreenHetero uses curve fitting to construct relational equations as a performance projection for each workload on each server platform. The objective of the solver is to maximize the overall performance of rack servers by finding the optimal value of power allocation ratio. Once the ratio is determined, the power consumption can be controlled at the server level by the power state such as DVFS and power saving state like sleep and hibernation. Although we can get a relation equation using the database as just mentioned. The scheduler cannot always guarantee the optimal power allocation result because the information from the profiling data is limited in the training run and can be less accurate. So the optimization operations include adding new relation projections and updating existing database. In the evaluation part, we choose up to 16 data center workload. We use 6 different server platforms and 5 different power management policies for comparison. These figures present the performance and power profile result. As we can see, GreenHetero outperforms the uniform policy for the most of scheduling epochs in case B and C when the renewable power supply is insufficient. The power source are batteries and the power grid. GreenHetero achieves up to 50% performance gain over uniform. In case A, the performance result is very close. The renewable power can independently support the load and the extra power will be charged into the battery. When the power supply varies, the ratio changes accordingly to achieve the best performance. Also, we analyze the impact of workload types. As we can see, for different workloads, GreenHetero can achieve performance improvement by 1.2 to 2.2 times and average EPU improvement by 2.2 times over uniform strategy. Finally, we evaluated the impact of different combinations of server configurations using representative workloads, especially for combination 6, due to the large difference in computing performance between GPU and CPU. The performance improvement by GreenHetero can be up to 4.6 times. Let's make a conclusion. In this work, we first analyze the impact of different renewable power allocation schemes. Then we propose GreenHetero, a dynamic power allocation framework. And our experimental results show that our solution can improve the average performance by 1.2 to 2.2 times. And thanks for your attention.